What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this. You're drifting through space when suddenly, the stars around you begin to warp. The fabric of reality twists, and before you can react, you're pulled into an abyss so powerful, not even light can escape. Time slows to a crawl, the laws of physics as you know them gone. This isn't science fiction. This is a black hole, one of the most terrifying and mesmerizing phenomena in the cosmos. And here's the wild part. We've only begun to scratch the surface of understanding them. Black holes are the universe's ultimate enigmas, cosmic monsters that warp space, freeze time, and defy every rule we've ever learned. They're not just holes in space, they're gravitational prisons, time machines, and maybe even gateways to other dimensions. For decades, they existed only in theory until science caught up with the math, and we finally saw one, a shadowy ring of fire 490 quadrillion miles away. But that image, that was just the beginning. The more we learn, the more we realize how little we truly know. That's where this video comes in. We're about to dive deep into 30 jaw-dropping facts about black holes, facts that will shatter your perception of reality. Did you know a black hole could turn you into a noodle of atoms in seconds, or that some might be hiding entire universes inside them? We'll explore how they bend light like a funhouse mirror, why they might hold the key to time travel, and what happens when two of them collide. This isn't just a list, it's a journey to the edge of physics itself. So buckle up. By the time we're done, you'll never look at the night sky the same way again. Black holes might sound like giant cosmic sinkholes, but they're anything but empty. The truth is far stranger. Imagine crushing the entire mass of our sun into a sphere just 6 miles wide. That's the kind of mind-bending density we're talking about. At their core lies the singularity, a point where gravity becomes infinite and the laws of physics as we know them simply break down. Think of it like a cosmic traffic jam where space and time collide, creating a one-way street where nothing, not even the fastest thing in the universe, light, can reverse course. Here's a way to picture it. If the sun suddenly turned into a black hole with the same mass, Earth wouldn't get sucked in like a marble down a drain. Instead, we'd keep orbiting as usual, just in total darkness. That's because black holes aren't sucking matter in like a vacuum cleaner. Their gravity works just like any other objects, only unimaginably more intense up close. Step 2, near the event horizon, though, and the real nightmare begins. This invisible boundary is the point of no return, where gravity's grip becomes so strong that even time starts stretching like taffy. 1 second for you could mean years passing for someone watching from afar. It's not a hole, it's a place where the universe itself folds inward, rewriting the rules in ways that still baffle scientists. Black holes aren't one-size-fits-all cosmic oddities. They range from tiny to unimaginably massive, each with its own eerie origin story. The smallest, known as stellar mass black holes, are born from the violent deaths of massive stars. When a star at least 20 times heavier than our sun runs out of fuel, it doesn't just fade away, it explodes in a supernova so powerful that the core collapses inward, crushing itself into a space smaller than a city. The result, a gravitational trap with the mass of several suns packed into a space just a dozen miles wide. Then there are the giants lurking at the heart of nearly every galaxy, supermassive black holes. These monsters weigh millions, even billions of times more than our sun, with event horizons so vast they could swallow our solar system whole. How they grow so enormous is still a mystery. Some might form from the merger of countless smaller black holes, while others could be ancient relics from the early universe, feasting on gas and stars for billions of years. Sandwiched between these extremes are the elusive intermediate black holes, cosmic middleweights that have long puzzled astronomers. Far rarer than their smaller or larger cousins, these could be the missing link in understanding how supermassive black holes form. Imagine a black hole with the mass of hundreds or thousands of suns. drifting silently through galaxies, invisible except for their gravitational tug on nearby stars. What's truly mind-bending is how differently these black holes behave. A stellar mass black hole might shred a star into glowing ribbons, while a supermassive one could warp the orbits of entire star clusters. Size isn't just a detail, it's the difference between a cosmic pebble and a gravitational tsunami. Hold onto your seat because near a black hole, time itself becomes fluid. Einstein's theory of relativity revealed something astonishing. Gravity doesn't just pull on objects, it bends time. The stronger the gravity, the slower time ticks. Picture two identical clocks, one placed on Earth, the other near a black hole's event horizon. The clock near the black hole would run noticeably slower, as if the universe itself hit the brakes. This isn't a thought experiment, it's a real phenomenon called time dilation, proven by atomic clocks on fast-moving jets and satellites orbiting Earth. But near a black hole, the effect becomes extreme. Take the famous twin paradox. If one twin ventured close to a black hole while the other stayed home, the traveling twin might return only a few years older while decades or even centuries passed on Earth. This played out dramatically in Interstellar, where astronauts on a planet near the black hole Gargantua experienced mere hours, while their crewmate orbiting farther away aged 23 years. It wasn't just Hollywood magic, it was grounded in real physics. Here's the wild part: time dilation isn't just about speed, like in Interstellar, but about gravity's grip. The closer you get to a black hole's singularity, the more space-time stretches like taffy, making seconds drag into years for anyone watching from a distance. Even your body would experience time differently. Your feet, closer to the black hole's pull, would age slower than your head. It's a universe where gravity doesn't just bend space, it rewrites time. And the deeper we explore this, the clearer it becomes. Black holes aren't just cosmic vacuum cleaners, they're time machines. If you ever find yourself unlucky enough to fall into a black hole, death wouldn't come quickly, it would come creatively. Long before you reached the event horizon, gravity's tidal forces would pull off something called spaghettification, a process as horrifying as it sounds. Picture this: your feet, closer to the black hole's crushing grip, would feel a stronger gravitational pull than your head. That difference in force would stretch you like taffy, elongating your body into a thin, noodle-like strand of atoms. Meanwhile, the sideways compression from the black hole's immense gravity would squeeze you from all directions, turning you into a cosmic piece of spaghetti. But the nightmare doesn't stop there. Every part of you, your bones, your organs, even individual molecules, would experience the same gruesome stretching. The extreme tidal forces would rip apart the very bonds holding matter together, reducing you to a stream of subatomic particles spiraling toward the singularity. This isn't just theoretical, we've actually observed stars suffering the same fate. When a star drifts too close to a black hole, astronomers have watched it stretch into glowing arcs of plasma before being devoured entirely. What makes spaghettification so terrifying is the sheer scale of the forces at play. Near a stellar mass black hole, tidal forces become lethal just outside the event horizon, meaning you'd be shredded before you ever crossed the point of no return. But with a supermassive black hole, the difference in gravity across your body is more gradual. You might actually survive crossing the event horizon, only to face an even more bizarre fate deeper inside, where physics as we know it ceases to exist. Either way, one thing's certain: in the presence of a black hole, the universe has a brutal sense of humor. A black hole doesn't just sit there, it can spin so fast it twists the fabric of reality itself. These cosmic dynamos, called Care black holes, don't just swallow everything in their path, they drag space-time along with them like a whirlpool in a cosmic river. The faster they spin, the more extreme the effect becomes, warping space so severely that even light struggles to escape their gravitational vortex. Some of these black holes rotate at nearly 99% the speed of light, a mind-bending velocity that distorts the universe around them into bizarre new shapes. At the heart of this chaos lies a region called the ergosphere, an oval-shaped zone outside the event horizon where space-time is dragged so violently that nothing can stand still. Imagine trying to swim against a current moving faster than you ever could. Even light itself gets caught in this cosmic undertow. But here's the wild part: the ergosphere isn't just a destructive force. It's also a potential goldmine of energy. Scientists theorize that if we could harness the rotational energy of a spinning black hole, it could provide more power than all the stars in our galaxy combined. The process, known as the Penrose process, involves dropping matter into the ergosphere in just the right way to steal energy from the black hole's spin, like skimming energy from a runaway cosmic turbine. What makes this even more astonishing is that we've already detected black holes spinning at these unbelievable speeds. Take the supermassive black hole at the center of galaxy M87, the first one ever imaged by humanity. Observations suggest it's rotating fast enough to flatten space-time around it like a pancake, and if an advanced civilization ever figured out how to tap into that spin, they could power interstellar travel, megastructures, or even entire cities for billions of years. A spinning black hole isn't just a destructive force, it's a universe-sized battery waiting for someone to flip the switch. Stephen Hawking stunned the physics world when he proposed something seemingly impossible: black holes might not be eternal. According to his groundbreaking theory, these cosmic monsters actually leak particles over time, slowly shrinking until they vanish in a final burst of energy. This phenomenon, now called Hawking radiation, turns everything we thought about black holes on its head. Here's how it works. Quantum mechanics tells us that empty space isn't truly empty. Microscopic particles constantly pop in and out of existence, appearing as particle-antiparticle pairs before annihilating each other in an instant. But near a black hole's event horizon, something bizarre happens. If these pairs form right on the edge, one particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this slow leak adds up, causing the black hole to lose mass and eventually evaporate entirely. The implications are staggering. A black hole the mass of our Sun would take longer than the current age of the universe to evaporate. But smaller black holes, they'd vanish much faster, and their final moments would be spectacular. A black hole with the mass of a mountain might explode with the energy of 1,000,000 hydrogen bombs, lighting up the cosmos like a firework. This isn't just theoretical. If tiny primordial black holes formed in the early universe, we might one day detect their explosive deaths as gamma-ray bursts in deep space. Yet Hawking radiation also creates a paradox that still keeps physicists awake at night. The particles escaping carry no information about what fell into the black hole, which clashes with quantum mechanics' rule that information can never be destroyed. This information paradox has sparked decades of debate, with some suggesting the event horizon might be a seething firewall of energy, while others propose hidden dimensions or holographic universes as solutions. One thing's certain: Hawking's discovery proved that black holes aren't the eternal prisons we once imagined. They're dynamic, decaying, and far stranger than even Einstein predicted. Towering silently at the heart of our Milky Way lies Sagittarius A, a supermassive black hole with the weight of 4 million suns, yet it's barely flickering. This cosmic behemoth should be devouring stars and belching radiation, but right now it's practically napping. Don't let the calm fool you, though. Geological evidence suggests that just a few million years ago, a blink in cosmic time, our galactic center erupted in a cataclysmic outburst so powerful it lit up clouds near Earth like a neon sign. Today, that same monster barely nibbles on wisps of gas, leaving astronomers puzzled by its table manners. In 2022, humanity finally got its first direct look at this sleeping giant. Using a global network of telescopes called the Event Horizon Telescope, scientists captured an image of Sagittarius A's shadow, a glowing ring of light warped by spacetime itself. The photo revealed something unexpected. Despite its mind-bending mass, our galaxy's black hole consumes material at a rate so slow, it's like a person eating 1 grain of rice every million years. What keeps this titan so quiet? The answer might lie in its dining habits. Unlike smaller black holes that violently shred stars, Sagittarius mostly feeds on thin, scattered gas clouds. Without large meals, it lacks the energy for spectacular outbursts, but patience is key. Astronomers have caught it occasionally burping X-rays after swallowing a rogue gas cloud or unlucky star. And when it does wake up, the fireworks could outshine every star in the sky. Some theories even suggest that ancient bursts from Sagittarius might have influenced life on Earth by altering our planet's radiation levels. Here's the cosmic irony: the same gravity that could tear planets apart also holds our galaxy together. Every star in the Milky Way, including our Sun, dances to the silent tune of this invisible Titan's pull. Without it, we'd drift into the cosmic void, proof that sometimes the most terrifying forces are also the glue keeping our universe intact. In the darkest corners of the cosmos, black holes don't just lurk, they light up the universe in ways that defy imagination. Quasars, the most luminous objects ever discovered, are proof of that. These brilliant beacons shine with the energy of 1 trillion suns, outshining entire galaxies from billions of light years away. And at the heart of each one, a supermassive black hole feeding on a cosmic buffet of gas, dust, and stars with such ferocity that it turns destruction into creation. Picture a black hole so ravenous that it devours the equivalent of a sun's worth of material every year. As matter spirals inward at nearly light speed, friction heats it to millions of degrees, creating a swirling disk of supercharged plasma brighter than anything else in existence. Some of this material doesn't fall in, it gets funneled into jets of energy shooting out from the black hole's poles at nearly the speed of light, stretching hundreds of thousands of light years into space. These jets act like interstellar spotlights, visible across the universe long after the black hole itself has vanished from view. What's truly astonishing is how quasars served as cosmic time capsules. Because light takes time to travel, the most distant quasars we see are snapshots of the universe's infancy, some burning bright when the cosmos was less than 1 billion years old. Without them, we might never have grasped how quickly supermassive black holes formed after the Big Bang. The fact that quasars existed so early challenges everything we thought we knew about how these giants grow. Yet quasars aren't just relics of the past. Even today, galaxies with active black holes, their quieter cousins called blazars and Seyfert galaxies, continue to sculpt the cosmos. Their radiation can ignite star formation in distant clouds or sterilize entire galaxies, preventing life from ever taking hold. A quasar's light might fade over eons, but its legacy reshapes the universe forever. Some black holes don't just devour matter, they blast it back into the cosmos with the force of 1 billion supernovas. These are relativistic jets, narrow beams of superheated plasma screaming from the black hole's poles at nearly the speed of light. Stretching for millions, sometimes billions of light years, they're the universe's largest particle accelerators, capable of launching material clear across entire galaxy clusters. Picture a fire hose of energy so powerful it could vaporize entire solar systems in its path. And yet, these jets also sculpt the very galaxies they inhabit. The physics behind them is just as breathtaking as their scale. As a black hole feasts on swirling disks of gas, magnetic fields twist into cosmic tornadoes around its poles. These fields funnel some of the infalling matter away from the event horizon, accelerating it to velocities so extreme that particles within the jets experience time at a fraction of the speed we do. The result, a beam of radiation and particles energetic enough to outshine entire galaxies. One of the most famous examples, the quasar 3C273, boasts jets stretching over 2 million light-years, 20 times the diameter of the Milky Way. But these jets aren't just cosmic spectacles, they're galactic architects. When they slam into surrounding gas clouds, they can trigger shock waves that compress matter, sparking the birth of new stars, or conversely, sterilize regions of space by stripping planets of their atmospheres with intense radiation. Astronomers have even found evidence that jets from supermassive black holes might regulate star formation across entire galaxies, acting like cosmic thermostats that switch stellar nurseries on or off. The truly unsettling part, Earth isn't immune. If our galaxy's dormant supermassive black hole, Sagittarius A, were to awaken and fire a jet in our direction, the high-energy particles could bathe our planet in lethal radiation, rewriting the history of life in an instant. Fortunately, its jets, if it ever produces them, would likely point harmlessly into intergalactic space. Still, it's a stark reminder that black holes aren't just distant oddities. Their influence stretches far beyond their event horizons, shaping the fate of everything in their path, one relativistic jet at a time. Crossing the event horizon of a black hole sounds like an instant death sentence, but if the black hole is big enough, you might not even realize you've passed the point of no return. Here's the catch: size matters immensely. With a smaller stellar mass black hole, tidal forces would rip you apart long before you reach the event horizon, stretching you into a strand of atoms in a process called spaghettification. But step toward a supermassive black hole like the one at the center of our galaxy, and the difference is night and day. Because its gravity is spread over such an enormous volume, the tidal forces near its event horizon are far weaker. You could cross it without immediately being torn to shreds, at least at first. Inside, the laws of physics as we know them would start to unravel. The event horizon isn't a solid wall, it's an invisible boundary where escape becomes impossible. If you were falling feet first into a supermassive black hole, your feet would feel a slightly stronger gravitational pull than your head, but the difference might be mild enough that you'd survive the crossing. Looking outward, you'd see the universe distort in bizarre ways. Light from stars behind you would bend into a shrinking circle of brightness, warped by the black hole's gravity until it appeared as a single point, then blinked out entirely. Meanwhile, ahead of you, the black hole's crushing singularity would loom, though by then you'd be too deep for any signals to escape and tell the tale. The real nightmare begins once you're past the event horizon. Time and space swap roles. Instead of moving forward through time, you're drawn inevitably toward the singularity, just as we're always moving toward the future in the outside universe. The singularity itself is where physics completely breaks down, a point of infinite density where matter is crushed beyond recognition, and even Einstein's equations fail. Some theories suggest you might encounter a firewall of intense radiation, while others propose wild ideas like wormholes or new universes hidden inside. The truth, nobody knows for sure. What we do know is that once you cross that threshold, there's no turning back, just a one-way trip into the greatest unknown in the cosmos. Here's the ultimate irony. While you might survive the crossing in theory, the universe itself would conspire against your story ever being told. Any signals you tried to send would be redshifted into oblivion, your final moments stretched across eternity from an outside observer's perspective. The black hole wouldn't just consume you, it would erase your existence from the cosmic record, leaving behind only gravity's silent signature. Black holes might not just be cosmic dead ends, they could be the universe's ultimate shortcuts. The idea isn't just science fiction. Einstein's equations actually allow for the existence of tunnels through space-time called Einstein-Rosen bridges, better known as wormholes. Picture a black hole singularity not as a crushing-in point, but as a gateway, a cosmic subway linking two distant points in space, or even different universes entirely. The math suggests that under the right conditions, the extreme warping of spacetime inside a black hole could theoretically connect to another region, creating a bridge where matter might, just might, pass through unharmed. Of course, there's a catch. Even if a black hole did function as a wormhole, surviving the trip would require forces beyond anything we know. The immense tidal forces near the singularity would likely shred anything attempting the journey, and the wormhole itself would be unstable, snapping shut in an instant unless propped open by exotic matter with negative energy, something we've never observed in nature. That hasn't stopped physicists from dreaming, though. Some theories suggest rotating black holes with their twisted spacetime might offer slightly safer passage, while others propose that advanced civilizations could stabilize wormholes using unfathomable technology. Sci-fi loves this idea, and for good reason. From Interstellar's Gargantua to Stargate's portals, wormholes offer a tantalizing workaround for interstellar travel. But reality is far messier. Even if black holes did connect to other places, sending a probe, let alone a person, through one would be like threading a needle in a hurricane. The radiation, the gravitational forces, the sheer unknowns of what lies on the other side make it a one-way trip into the realm of speculation. Still, the possibility lingers, teasing us with cosmic what-ifs. Could some black holes be backdoors to other dimensions? Might the universe be threaded with hidden passageways we just haven't found yet? For now, it remains one of physics' greatest mysteries. A reminder that even our wildest theories might just be scratching the surface of reality's deepest secrets. The universe began with a bang, but could it end with a cosmic crunch? Among the most haunting theories in cosmology is the idea that black holes might one day consume everything, turning the cosmos into a graveyard of singularities. This apocalyptic scenario, known as the Big Crunch, flips the Big Bang on its head. Instead of expanding forever, the universe would eventually reverse course, collapsing inward as galaxies, stars, and even space-time itself succumb to gravity's relentless pull. At the heart of this theory lies an unsettling truth. Black holes aren't just celestial anomalies, they could be the universe's ultimate fate. Imagine a future trillions of years from now, where the last stars have burned out and galaxies drift like ghosts in the void. One by one, black holes would begin merging, swallowing the remnants of dead stars and planets in an endless feeding frenzy. Over mind-numbing timescales, these monsters would grow larger and larger, their event horizons stretching to engulf entire galactic clusters. Eventually, all matter in existence could coalesce into a single, unfathomably massive black hole, a final singularity containing everything that ever was. Some models even suggest this super black hole might trigger a new Big Bang, recycling the universe in an infinite loop of creation and destruction. But the Big Crunch isn't the only grim finale on the table. Another theory, heat death, paints an eerily quiet end. As the universe expands, energy spreads so thin that stars can no longer form. Black holes evaporate via Hawking radiation, and space-time itself grows cold and dark. Here's the twist: even in this frozen wasteland, black holes would be the last survivors. They'd outlast galaxies by trillions of years, slowly leaking energy until they too vanish, leaving behind a lifeless cosmos where not even light remains. The chilling connection between these theories: entropy, the universe's measure of disorder. Black holes are entropy's ultimate expression, swallowing information and energy into irreversible chaos. Whether through a fiery crunch or a silent fade, their role in the cosmos's in-game reveals a profound truth. Gravity always wins, and in that final act, the universe might just complete the circle, from singularity to singularity, with black holes as both its architects and executioners. Most black holes stay anchored at the center of galaxies, but some go rogue, drifting through the cosmic void like gravitational nomads. These outcasts form when black holes collide, and the resulting kick is so powerful, it flings the merged object clear out of its galaxy at speeds up to 5 million miles per hour. Picture the universe's ultimate cannon shot, a black hole weighing millions of suns, hurled into intergalactic space with enough force to escape its galaxy's gravity forever. Detecting these invisible drifters is like finding a needle in a billion haystacks. Since rogue black holes emit no light, astronomers hunt them by spotting the telltale warping of starlight as they pass in front of distant stars, a phenomenon called gravitational microlensing. The black hole's gravity bends the star's light like a magnifying glass, briefly brightening it before moving on. In 2011, one such event revealed a rogue black hole roughly 7 times the mass of our Sun, drifting silently through the Milky Way's spiral arms. Now for the unnerving part. If one wandered into our solar system, we might not know until it was too late. Unlike a star, a rogue black hole wouldn't light up the sky. It would reveal itself through subtle gravitational chaos. Planets would veer off course without explanation. Earth's orbit might stretch or wobble as the unseen monster's pull warped our solar system's delicate balance. Long before we saw its shadow, we'd feel its presence in the way comets mysteriously changed paths or asteroids suddenly scattered. The odds are astronomically low, but the cosmic wilderness is full of surprises. Rogue black holes remind us that the universe isn't just vast, it's unpredictably alive with invisible giants lurking in the dark between the stars. When two black holes collide, the universe doesn't stay silent, it rings like a bell. In 2015, scientists at LIGO detected something extraordinary: gravitational waves rippling through space-time itself, created by a pair of black holes spiraling into each other a billion light-years away. These weren't just faint tremors, they were the violent echoes of a cosmic merger, carrying secrets about the black hole's final moments. Imagine dropping a pebble into a still pond. The ripples spread outward, fading as they go. Now replace that pebble with two black holes heavier than 30 suns, crashing together at half the speed of light. The resulting shockwaves distort space-time itself, stretching and squeezing everything in their path, including the fabric of reality on Earth. What makes these waves so revealing is their unique ring-down signature. Just after the collision, the newly merged black hole vibrates like a struck gong, emitting gravitational waves at precise frequencies that slowly fade, a phenomenon called quasi-normal modes. By analyzing these waves, physicists can deduce the black hole's mass, spin, and even shape. The data tells a story: two predators circling each other in a death spiral, merging into one, then settling into silence as the final echoes dissipate into the cosmos. Hearing these waves adds another layer of awe. LIGO team converted the gravitational ripples into sound waves, producing an eerie chirp, a rising tone that peaks as the black holes merge, followed by a rapid decay. That chirp isn't just a cosmic curiosity, it's a direct line into the heart of one of the universe's most violent events. The pitch reveals the black hole's masses, while the duration hints at how far away they were. Future detectors could capture even more detail, like the thud of a black hole slamming into a neutron star or the deep boom of supermassive black holes merging in distant galaxies. What's startling is how much these echoes reveal. From a billion light-years away, we've learned that black holes often spin wildly before merging, sometimes in opposite directions, like dancers spinning backward into a lethal embrace. Some collisions even kick the merged black hole clear out of its galaxy, sending it hurtling through space at millions of miles per hour. Each ripple is a cosmic telegram decoding the lives and deaths of objects we'll never see directly. And with every new detection, we're tuning into a universe that hums with the hidden music of black holes. For decades, scientists thought black holes were the universe's ultimate minimalist, objects so simple they could be described with just 3 features: mass, spin, and charge. This idea, known as the no-hair theorem, suggested that no matter how complex an object was before collapsing into a black hole, all its unique details, its hair, would be erased forever. Like cosmic amnesia, the singularity would scrub away any trace of what fell in, leaving behind a perfectly smooth, featureless void. but what if that's not the whole story? Recent breakthroughs hint that black holes might be far more expressive than we ever imagined. Quantum physics throws a wrench into this tidy picture. Near the event horizon, the rules of the microscopic world take over, and particles popping in and out of existence could leave subtle imprints on a black hole's structure. Think of it like static on an old television, tiny fluctuations that might encode information about the black hole's history. Some theories even suggest that black holes could develop quantum hair, faint but detectable traces of what they've consumed. These wouldn't be physical strands, of course, but patterns in the way spacetime itself vibrates or warps, cosmic fingerprints unique to each black hole. The implications are staggering. If black holes do retain some form of memory, it could solve one of physics' greatest paradoxes, the information problem. According to quantum mechanics, information can never be destroyed, yet the no-hair theorem seemed to demand exactly that. Quantum hair might bridge the gap, preserving data in ways we're only beginning to understand. Imagine a black hole not as a cosmic shredder, but as a vault storing secrets in the very fabric of its gravity. Evidence is mounting. In 2022, researchers studying gravitational waves noticed anomalies in the echoes of black hole mergers, subtle ripples that didn't match predictions based on the no-hair theorem. Could these discrepancies be glimpses of quantum hair? Future observatories like the planned LISA space mission might finally spot the telltale signatures. If they do, it would rewrite our understanding of black holes from the ground up, proving they're not just simple voids, but complex objects with hidden stories to tell. The universe's darkest enigmas might yet have a few surprises left. Black holes don't just swallow light, they twist it into cosmic funhouse mirrors, bending the very fabric of reality to create illusions that defy logic. This mind-bending phenomenon, called gravitational lensing, occurs when a black hole's immense gravity warps spacetime so severely that light passing nearby gets dragged off course. Imagine a bowling ball placed on a trampoline. The heavier the ball, the deeper the dip, and the more any rolling marble will curve around it. Now replace the bowling ball with a black hole and the marble with light from a distant star. The result, light doesn't travel in a straight line anymore. It follows the curve of distorted spacetime, creating surreal visual effects that astronomers can actually observe. One of the most striking examples is the Einstein ring, a perfect halo of light formed when a black hole aligns precisely between Earth and a distant galaxy. The galaxy's light gets stretched and bent around the black hole like water swirling down a drain, forming a luminous circle in the sky. In some cases, the lensing is so extreme that a single galaxy appears as multiple mirrored images around the black hole, like reflections in a shattered kaleidoscope. The Hubble Space Telescope has captured these ghostly duplicates in stunning detail, galaxies split into arcs, smears, and even complete rings, all by the invisible hand of gravity. But the real magic happens when the alignment isn't perfect. Light from stars directly behind a black hole gets stretched into bizarre shapes, long, thin streaks or smeared halos that look nothing like their source. Simulations show how a black hole could turn a simple spiral galaxy into a nightmarish funhouse reflection, warping its arms into twisted loops or splitting its core into a cross-shaped mirage. These distortions aren't just artistic guesses, they're precise predictions of Einstein's general relativity, proven correct time and again by telescopes peering into the depths of space. What's truly astonishing is how lensing reveals the unseen. Black holes themselves are invisible, but their gravitational grip on light betrays their presence. By studying these cosmic optical illusions, astronomers have mapped dark matter, measured the mass of distant black holes, and even glimpsed galaxies so far away their light has traveled nearly the entire age of the universe to reach us. Gravitational lensing turns black holes into nature's ultimate telescopes, magnifying objects we'd otherwise never detect, proving once again that in the cosmos, even the darkest forces can illuminate the unimaginable. In the cosmic dance of destruction, some stars don't flee black holes, they waltz with them in a deadly embrace. Take Cygnus X1, one of the most famous black hole star pairs ever discovered. Here, a supergiant star 20 times heavier than our Sun orbits a black hole so closely that a year on this system lasts just 5.5 Earth days. The star isn't just a passive partner, it's actively being devoured, its outer layers siphoned away by the black hole's gravity in a swirling stream of superheated gas. This isn't a slow process. Material races toward the event horizon at nearly a third the speed of light, heating up to millions of degrees and unleashing torrents of X-rays visible across the galaxy. What makes these systems so fascinating is how they reveal black holes in action. Unlike solitary black holes that lurk invisibly in space, these X-ray binaries broadcast their presence with violent flares. As gas from the star spirals into the black hole's accretion disk, friction heats it to unimaginable temperatures, creating a visible glow that pulses like a cosmic strobe light. Astronomers can actually track the star's orbit by these X-ray bursts, mapping the black hole's gravitational pull like detectives following breadcrumbs. In Cygnus X1's case, these observations prove the black hole's mass 15 times that of our Sun, locked in a gravitational tango with its stellar companion. But the star isn't just a victim, it's fighting back. Some of the stolen gas doesn't make it past the event horizon. Instead, it gets funneled into jets blasting outward at near light speed, punching holes through surrounding space like a cosmic blowtorch. These jets can stretch for light years, carving out bubbles in interstellar gas and even influencing star formation in their path. It's a twisted symbiosis. The black hole feeds on the star, while the star's stolen energy reshapes the galaxy around them. The strangest part, these systems might be more common than we thought. Recent surveys suggest thousands of similar black hole star duos could be hiding in our galaxy, their X-ray flares too faint or too brief for current telescopes to catch. Each one offers a front-row seat to astrophysics in its most extreme form, where gravity's grip bends not just space but the very fate of stars. And as astronomers discover more of these deadly dances, they're realizing, in the universe's grand ballet, sometimes the most spectacular moves happen between partners locked in a fight for survival. At the far reaches of the observable universe lurks a monster so vast it defies comprehension. Ton 618, the largest black hole ever discovered. This cosmic colossus weighs in at a staggering 66 billion times the mass of our Sun, a gravitational titan whose event horizon stretches farther than the distance from our Sun to Pluto 40 times over. To put that into perspective, if you replaced our Milky Way's central black hole, Sagittarius A, with Ton 618, its event horizon would engulf every planet, asteroid, and comet out to the Kuiper belt without breaking a sweat. What makes Ton 618 so baffling isn't just its size, it's the sheer audacity of its existence. This behemoth lives in the heart of a distant quasar, shining with the brightness of 100 trillion suns as it devours matter at an unfathomable rate. The energy it releases is so immense that astronomers detected its light from over 18 billion light-years away, a relic from when the universe was still in its infancy. Yet here's the real puzzle. Black holes this massive shouldn't theoretically exist so early in cosmic history. Current models suggest supermassive black holes grow slowly over billions of years by merging with others and feasting on gas. But Ton 618 defies that logic. It's as if the universe cheated, spawning a fully formed giant when it was barely a toddler. Comparing Ton 618 to our own galactic center's black hole is like stacking a skyscraper next to a pebble. Sagittarius A, with its respectable 4 million solar masses, could orbit Ton 618's event horizon like a speck of dust circling a whirlpool. The gravitational influence of a black hole this size is almost incomprehensible. Stars thousands of light-years away would dance to its tune, their orbits warped by its sheer presence. If you stood on a planet near Ton 618's accretion disk, the sky would be dominated by a swirling maelstrom of light so bright it'd outshine every star in the night sky combined. Yet even this cosmic leviathan has limits. Despite its staggering mass, Ton 618 isn't infinitely hungry. Its accretion disk, the superheated ring of doomed matter spiraling inward, stretches so wide that gas at the outer edges takes centuries to reach the event horizon. Some of that material doesn't fall in at all. Instead, it's funneled into jets of plasma shooting out at nearly light speed, visible across the cosmos as twin beams of raw energy. These jets are so powerful they can shape entire galaxies, heating interstellar gas and suppressing star formation for millions of light years around them. The discovery of Ton 618 forces us to rethink how black holes grow. Did it form from the direct collapse of a primordial gas cloud in the early universe? Or was it born from a chain reaction of mergers between smaller black holes in a densely packed galaxy cluster? Whatever the answer, one thing's certain: this gravitational giant proves that the universe loves breaking its own rules. And somewhere out there, even larger black holes might be waiting hidden in the darkness, bending the fabric of reality to their will. What if the answer to one of cosmology's greatest mysteries has been hiding in plain sight, or rather, in the darkest corners of space? For decades, scientists have grappled with dark matter, the invisible glue holding galaxies together. Its gravitational pull bends light and molds the cosmos, yet it emits no light, no radiation, nothing we can directly detect. But here's a radical idea. What if dark matter isn't made of exotic particles at all? What if it's actually an army of ancient black holes born in the chaos of the early universe? These hypothetical objects, called primordial black holes, are unlike any black holes we know. They wouldn't form from collapsing stars, they'd be relics of the Big Bang itself, forged in the universe's first second when denser patches of space-time collapsed under their own gravity. Ranging in size from a speck of dust to a mountain's mass, these black holes could be scattered everywhere, drifting between stars like invisible ghosts. Since they'd emit no light and rarely interact with matter, they'd be nearly impossible to spot, yet their collective gravity could explain the mysterious tug we attribute to dark matter. The math is surprisingly compelling. If just a fraction of the early universe's energy condensed into primordial black holes, say, 1 for every 1,000 cubic light-years of space, their combined mass would match dark matter's gravitational footprint perfectly. Unlike theoretical dark matter particles, which remain frustratingly elusive in underground detectors, primordial black holes don't require new physics. They'd simply be hiding in Einstein's equations all along. But how could we ever prove they exist? Astronomers have devised clever hunts. When a primordial black hole passes in front of a distant star, its gravity briefly magnifies the star's light, an effect called microlensing. Surveys like the Subaru telescope's HSC have scanned millions of stars for these telltale flickers, placing tight limits on how many such black holes could lurk in our galaxy. Other researchers study the cosmic microwave background, looking for subtle scars left by primordial black holes forming in the infant universe. The most tantalizing clue might come from gravitational waves. Tiny black holes merging in the early cosmos would create high-frequency ripples far beyond LIGO current reach, but future observatories could detect their echoes. Even more provocative, some primordial black holes might still exist today, hiding in the outer solar system. Their gravity could explain oddities like the orbits of distant Kuiper belt objects, or even legendary anomalies like Planet 9. Of course, the theory isn't perfect. If too many primordial black holes existed, they disrupt neutron stars or warp the cosmic microwave background in ways we don't observe. Yet recent studies suggest a sweet spot: black holes around the mass of an asteroid could evade these constraints while still accounting for dark matter's pull. It's a cosmic balancing act where these ancient objects must be rare enough to stay hidden, but numerous enough to shape the universe. Whether or not primordial black holes solve the dark matter puzzle, their possibility reshapes how we see the cosmos. The universe's darkest secrets might not lie in undiscovered particles, but in black holes older than stars themselves, silent witnesses to the Big Bang's fury, threading the galaxy like beads on an invisible string. And if they're out there, every shadowed corner of space just became infinitely more intriguing. Deep in the heart of the Perseus galaxy cluster, a supermassive black hole isn't just lurking, it's singing. In 2003, astronomers made an astonishing discovery. This cosmic giant was emitting pressure waves through the surrounding gas, creating vibrations that translate to a single, haunting musical note, a B-flat 57 octaves below middle C. That's so deep the human ear couldn't possibly hear it naturally. But when scientists scaled it up by quadrillions of times and slowed it down, the universe revealed an eerie, resonant hum that had been echoing through space for 2.5 billion years. This cosmic melody isn't produced the way sound normally travels. There's no air in space to carry vibrations. Instead, the black hole's immense gravity sends ripples through the superheated gas swirling around it, creating pressure waves that spread outward like ripples on a pond. Each wave takes tens of millions of years to complete one full oscillation, making this the longest, lowest note ever detected. If you could stand near this black hole, you wouldn't hear anything at all. Space's silence would remain unbroken. But the gas acts like a vast interstellar instrument, resonating with the black hole's gravitational pull to produce this unimaginably deep tone. What makes this discovery even more fascinating is how it challenges our perception of black holes. We often think of them as silent destroyers, but this one has been broadcasting its presence across the cosmos since before multicellular life existed on Earth. The note's pitch gives scientists crucial clues about the black hole's mass and the density of the gas surrounding it, a cosmic fingerprint revealing details that light alone couldn't show. Listen closely, and the implications grow stranger. If a black hole can sing, could others create harmonies? Some theorists suggest that colliding black holes might produce discordant tones before merging into a new frequency, a gravitational symphony playing on scales beyond human comprehension. Future observatories might even detect these cosmic chords, using them to map the invisible structure of the universe. But for now, the Perseus black hole's hum stands alone, a solitary, deep space area reminding us that the universe isn't just something we see. It's something we might one day learn to hear. Black holes don't just bend space, they shatter the rulebook of physics itself. At the heart of this chaos lies the infamous information paradox, a conflict so deep it pits Einstein against quantum theory in a cosmic courtroom battle. Here's the problem. Quantum mechanics insists that information, the fundamental blueprint of every particle, can never be destroyed. Yet black holes seem to do exactly that, swallowing stars, planets, and light without leaving a trace. When Stephen Hawking first realized this contradiction, he stunned the scientific community by declaring black holes must erase information, sparking a decades-long feud with physicists like Leonard Susskind, who refused to accept nature would break its own rules. The debate grew so heated, Hawking famously made a bet in 1997, wagering an encyclopedia because information can always be recovered, against fellow physicist John Preskill. But the plot thickened when Hawking later admitted defeat, sort of. His revised math suggested information might escape, but in such scrambled form it would be useless, like burning a library and claiming the smoke preserved every book. This didn't satisfy skeptics, who argued real information preservation requires meaningful retrieval. Enter the firewall paradox, a radical idea proposing the event horizon isn't a gentle threshold but a searing wall of energy that vaporizes anything crossing it. Picture falling toward what you think is a dark void, only to hit an invisible barrier hotter than a supernova, a cosmic keep-out sign that preserves information by destroying the intruder. Firewalls solve one problem by creating another. If they exist, they violate Einstein's principle that free-falling observers should experience nothing unusual at the event horizon, a cornerstone of general relativity. Theorists are now exploring wild alternatives, like holographic universes where information isn't lost but projected onto the black hole's surface like a cosmic DVD, or wormholes linking swallowed particles to outgoing radiation. Recent gravitational wave data even hints at mysterious echoes after black hole collisions, potential fingerprints of these exotic physics at work. The stakes couldn't be higher. If information truly vanishes, it undermines quantum theory's foundation. If it escapes, we might need to rewrite Einstein. Either way, black holes have once again proven to be the universe's ultimate rebels, testing our boldest ideas against the unforgiving laws of gravity. Imagine a black hole stripped of its shadowy cloak, no event horizon, no point of no return, just a naked singularity hanging in space like a cosmic exhibit. These hypothetical monsters, called naked singularities, are exactly what they sound like: black holes that don't play by the rules, exposing their infinitely dense cores to the universe without the usual veil of an event horizon. If they exist, they'd be the ultimate cosmic taboo, places where gravity becomes so extreme that space-time itself tears open, laying bare physics we can't even begin to comprehend. Einstein's equations actually permit these gravitational rebels, but there's a catch. Nature seems to abhor them. Most physicists believe the universe enforces something called cosmic censorship, a principle that insists singularities must always hide behind event horizons, like prisoners locked behind gravitational bars. The reasoning: without an event horizon, a naked singularity would unleash chaos. Time could become unpredictable, cause and effect might shatter, and the laws of physics as we know them would dissolve at its surface. Picture tossing a rock into one. In a normal black hole, the rock vanishes forever. But with a naked singularity, the rock could theoretically re-emerge anywhere, anyone, or even in multiple pieces at once. The debate hinges on how black holes form. When a massive star collapses, math suggests two possibilities. Either it forms an event horizon first, shielding the singularity from view, or, if it spins fast enough, the singularity might break free, going naked. Yet every black hole we've observed behaves as if it's decently clothed. Even the most extreme examples, like rapidly spinning Kerr black holes, keep their singularities safely hidden. Some scientists argue that cosmic censorship isn't just a suggestion. It's a fundamental law woven into the fabric of reality to prevent space-time from unraveling. Still, the possibility lingers. If a naked singularity did form, even briefly, its effects would rewrite physics textbooks. Light passing nearby could loop endlessly around it, creating ghostly multiple images of distant stars. Matter falling in might spit back out with impossible energy, violating every conservation law we hold sacred, and the singularity itself. It could be a portal to other universes, a factory for exotic particles, or a cosmic reset button, assuming it doesn't erase the very laws that allow it to exist. For now, naked singularities remain firmly in the realm of theory, but their potential existence is a thrilling reminder. The universe might still have secrets wilder than we've dared to dream. And if we ever found one, it wouldn't just change how we see black holes. It would force us to rebuild physics from the ground up. Black holes don't always announce their birth with a bang, some form in eerie silence, bypassing the fireworks of a supernova entirely. These cosmic anomalies, known as direct collapse black holes, defy the usual stellar life cycle where massive stars explode violently before collapsing. Instead, they skip the explosion phase altogether, imploding so rapidly and completely that not even light escapes the process. Picture a star so massive and dense that its own gravity becomes unstoppable, crushing it inward faster than the outer layers can react, leaving no time for a final, brilliant outburst. The result, a black hole born in shadow, emerging from the universe's darkest corners without so much as a cosmic whisper. These silent giants could hold the key to one of astronomy's biggest puzzles: how supermassive black holes grew so enormous so quickly in the early universe. Traditional models struggle to explain how black holes reached billions of solar masses when the cosmos was less than 1 billion years old. There simply wasn't enough time for them to grow gradually through mergers or steady feeding. But direct collapse black holes offer a tantalizing shortcut. Born from primordial gas clouds hundreds of thousands of times heavier than our Sun, they could have formed as seeds with masses tens of thousands of times greater than a typical stellar black hole, giving them a head start in the race to become supermassive. The conditions needed for these cosmic shortcuts are extreme. A direct collapse black hole requires a pristine environment, a cloud of pure hydrogen and helium, untouched by heavier elements that might fragment it into smaller stars. In the early universe, before the first stars polluted space with metals, such clouds could have collapsed directly under their own gravity, bypassing star formation entirely. The process would be swift and brutal. As the gas cloud condenses, its core reaches such insane densities that quantum pressure can't hold back gravity's crush. In a matter of centuries, a blink in cosmic time, it transitions from a diffuse cloud to a singularity, swallowing everything in its path. What's fascinating is how different these black holes behave compared to their supernova-born cousins. Without an explosion to scatter nearby gas, direct collapse black holes would sit in the heart of dense, fuel-rich regions, feasting on untouched material and ballooning in size at breakneck speeds. Some simulations suggest they could grow to supermassive proportions in just a few 100 million years, fast enough to explain the behemoths we see lighting up the early universe as quasars. Yet proving their existence remains a challenge. Unlike supernovas, which leave behind luminous remnants and shockwaves, direct collapse black holes leave no trace of their formation. Astronomers hunt for them indirectly, scouring the early universe for massive black holes with no obvious stellar progenitors, or searching for the unique chemical signatures their formation would imprint on surrounding gas. The James Webb Space Telescope, with its unparalleled infrared vision, might finally spot these elusive giants in their infancy, catching glimpses of primordial galaxies where black holes grew faster than the stars around them. If confirmed, direct collapse black holes wouldn't just solve a cosmic riddle, they'd rewrite the story of how the universe's most terrifying structures came to be. No explosions, no fireworks, just gravity's silent, inexorable victory, crafting monsters in the dark. Long before the first stars flickered to life, the universe may have been teeming with black holes smaller than atoms, fleeting cosmic specks born from the turbulence of creation itself. In the first chaotic moments after the Big Bang, when the entire cosmos was compressed into a seething, superheated soup, quantum fluctuations could have created pockets of density so extreme they collapsed into microscopic singularities. These primordial black holes wouldn't form from dying stars. They'd be relics of the universe's raw, unfiltered energy, condensed into gravitational knots when reality was barely a second old. What's astonishing is how different these ancient black holes would be from the ones we know today. Imagine a black hole lighter than a paperclip, yet packing the mass of an asteroid into a space trillions of times smaller than an atom. Their event horizons would be microscopic, so tiny they could pass through you right now without a trace, their gravity too weak to tug on even a single cell in your body. Yet according to Hawking radiation, the smallest of these primordial black holes wouldn't last long. Those with masses less than a small mountain would have evaporated in a blaze of gamma rays within the universe's first billion years, leaving behind only whispers of their existence. But here's the tantalizing possibility: some might still linger. If primordial black holes formed with slightly higher masses, say, as heavy as a skyscraper, their lifespans could stretch beyond the current age of the universe, hiding in plain sight as invisible cosmic wanderers. Astronomers have turned the cosmos into a giant hunting ground, searching for their elusive signatures. Some theories suggest these ancient black holes could explain mysterious gravitational microlensing events, where stars briefly brighten as unseen objects pass in front of them. Others propose they might be the hidden culprits behind oddities in the cosmic microwave background, ghostly fingerprints from the universe's infancy. The most electrifying idea: one of these primordial black holes could be lurking in our own solar system. If a wandering relic with the mass of a small planet drifted into orbit beyond Neptune, its gravity might account for the strange clustering of objects in the Kuiper Belt, behavior currently attributed to the hypothetical Planet 9. Unlike a planet, though, a primordial black hole wouldn't reflect sunlight or show up in telescopes. It would be a shadow within a shadow, detectable only by its gravitational pull on surrounding objects. Future missions equipped with ultra-sensitive detectors might finally spot these ghosts either by their subtle lensing effects or the bursts of Hawking radiation they emit as they evaporate. Whether they vanished eons ago or still drift unseen through the cosmos, primordial black holes force us to rethink the universe's earliest moments. They're reminders that black holes aren't just stellar gravestones, they could be cosmic fossils, carrying secrets from a time before stars, before galaxies, before light itself. And if we ever find one, it wouldn't just change our understanding of black holes, it would rewrite the story of how the universe began. Forget medieval alchemists, the real masters of turning cosmic trash into treasure are black holes and their violent celestial kin. When two neutron stars collide in a cataclysmic merger, they don't just create gravitational ripples, they become universe-scale forges, manufacturing precious metals like gold, platinum, and uranium in quantities that dwarf all the mines on Earth. The process starts in the final, frenzied moments before the collision, as these city-sized stellar corpses spiral toward each other at nearly light speed. Tidal forces rip them apart, ejecting neutron-rich material into space in glowing, radioactive plumes. Within these expanding clouds, something extraordinary happens, a rapid-fire nuclear reaction called the R process, where atomic nuclei capture free neutrons faster than they can decay. The result is cosmic alchemy on an unimaginable scale. In mere seconds, lighter elements get bombarded into heavier ones, climbing the periodic table all the way to gold and beyond. A single neutron star collision can produce enough gold to outweigh entire planets, scattering these freshly minted elements across interstellar space in shimmering waves of cosmic debris. Eventually, this material becomes incorporated into new stars, planets, and billions of years later, the jewelry on your finger, every gold wedding band or platinum record. It likely began in the violent death throes of colliding neutron stars, but here's where black holes enter the picture. Not all neutron star mergers leave behind a new neutron star. Many collapse directly into black holes, especially if their combined mass crosses a critical threshold. That means the very act of forging gold might also birth a black hole, making it the ultimate alchemical furnace, transforming stellar matter into both precious metals and gravitational monsters. The numbers are staggering. Astronomers estimate that the collision responsible for the gravitational wave event GW170817 ejected roughly 10 Earth masses worth of pure gold alone. That single cosmic smash produced more gold than humanity has mined in its entire history. Multiply that by the countless mergers across billions of years, and you realize black holes and their neutron star predecessors aren't just destroyers. They're the universe's most prolific jewelers, peppering galaxies with the raw materials for everything from smartphone circuits to Olympic medals. The next time you admire a gold necklace, consider this. Its atoms were likely born in a cataclysm so violent it warped space-time itself, a fleeting moment when the universe turned dying stars into treasure, then swallowed the evidence. Contrary to their name, black holes can be some of the brightest objects in the universe, not from their own light, but from the inferno of superheated gas spiraling toward oblivion. These glowing halos, called accretion disks, transform black holes from invisible voids into dazzling cosmic beacons, shining with the fury of millions of suns. Picture a donut spinning at nearly the speed of light, its surface scorched to temperatures hotter than the core of a star, a radiant death spiral where matter fights gravity's grip in a blaze of light. The physics behind this brilliance is both violent and beautiful. As gas, dust, or even entire stars drift too close to a black hole, they're torn apart by tidal forces, their remains forming a flattened disk that orbits the event horizon like water circling a drain. Friction within this disk heats the material to millions of degrees, causing it to emit X-rays and gamma rays, light so energetic it can outshine entire galaxies. The process is so efficient at converting matter into energy that accretion disks can achieve luminosities rivaling quasars, their glow visible across billions of light years. What's astonishing is the sheer diversity of these disks. Around stellar mass black holes, they might span mere hundreds of miles, yet glow white-hot as they devour a companion star's stolen gas. Supermassive black holes, on the other hand, host disks so vast they could engulf our solar system, their inner edges reaching temperatures high enough to vaporize diamond. The colors tell the story. Cooler outer regions emit red and infrared light, while the innermost zones blaze with ultraviolet and X-rays, creating a cosmic gradient of destruction. Some of the most extreme examples defy imagination. Take the black hole at the center of galaxy M87, the first ever imaged by humanity. Its accretion disk isn't just bright, it's twisted into a lopsided ring by the black hole's spin, bending light into a halo that looks like a surrealist painting of hell. Then there's the quasar 3C273, whose disk fires jets of plasma so powerful they stretch millions of light years into space, illuminating intergalactic gas like a celestial spotlight. Yet these disks aren't just cosmic spectacles, they're gold mines of information. By studying their light, astronomers can map a black hole's spin, measure its mass, and even test Einstein's theories under extreme gravity. The flickering patterns in their glow reveal turbulence and magnetic fields churning within, like reading hurricanes in the glow of a neon storm. And when a black hole feasts on a star, the disk's sudden flare acts like a cosmic alarm bell, alerting telescopes to witness gravity's most brutal show. So next time you think of black holes as dark, remember the truth. They're often crowned with light, a final, furious glow from matter sacrificing itself to the universe's hungriest monsters. Black holes aren't just defined by gravity. Some could carry an electric charge so powerful it rivals their cosmic pull. Enter the Nordstrom black hole, a theoretical monster that's not just crushing matter but crackling with electromagnetic fury. Picture a singularity wrapped in an event horizon, but with one terrifying upgrade: a charge strong enough to repel protons and snap atomic bonds from light years away. The math behind these charged leviathans isn't new. Einstein's equations allow for them, but their behavior defies everything we know about cosmic destruction. Unlike their neutral cousins, charged black holes don't just warp spacetime, they electrify it. Their event horizons split into two distinct layers, an outer boundary where gravity's grip becomes inescapable, and an inner Cauchy horizon, a zone where time and space lose all meaning. Step between these boundaries and the rules flip. Gravity's pull weakens while electromagnetism takes over, creating a nightmarish landscape where charged particles are yanked apart by forces trillions of times stronger than any magnet on Earth. Imagine trying to hold two repelling magnets together, except the magnets are stars and the force could shred planets. The real cosmic fireworks happen when matter dares to approach. A charged black hole's electromagnetic field would strip electrons from atoms long before tidal forces could spaghettify you, turning incoming gas into a swirling storm of supercharged plasma. This isn't just theoretical. Some models suggest these black holes could accelerate particles to near light speed, firing them into space like a cosmic railgun. The energy released could outshine quasars, with lightning bolts stretching across galactic distances. But here's the catch: nature might have ways to prevent these charged monstrosities from forming. Black holes tend to neutralize themselves over time, attracting enough opposite charges to balance out. That's why we've never observed one yet. In the chaotic early universe before stars and galaxies formed, conditions might have been just right for these electrified anomalies to exist, if only briefly. Some theories even propose microscopic charged black holes as dark matter candidates, zipping through space like invisible hypercharged bullets, the wildest possibility. A charged black hole's inner horizon might not be a death sentence, it could be a gateway. Calculations suggest crossing this boundary might let you glimpse regions of space-time normally hidden from the universe, though you'd still hit the singularity eventually. Whether they're cosmic relics or just mathematical curiosities, charged black holes remind us the universe's darkest corners might still be crackling with unseen energy. Most galaxies host a single supermassive black hole at their core, but sometimes cosmic collisions create monstrous pairs locked in a gravitational dance. Take OJ-287, a galaxy over 3.5 billion light-years away that doesn't play by the rules. At its heart, not one but two supermassive black holes orbit each other, the larger weighing 18 billion solar masses, making it one of the heaviest black holes ever discovered. Their gravitational tango is so precise, it acts like a cosmic clock, producing bright flashes of light every 12 years when the smaller black hole plows through the larger one's accretion disk, heating the gas to temperatures hotter than a supernova. These binary systems form when galaxies merge, their central black holes inevitably drawn together over millions of years. At first, they orbit at vast distances, but as they lose energy through gravitational waves and interactions with surrounding stars, they spiral closer, sometimes stalling just a few light-years apart in what astronomers call the final parsec problem. The pair in OJ-287 has beaten the odds, though, closing the gap to the point where their orbital period is now just 12 years. Each time the smaller black hole plunges through the disk of its colossal partner, it triggers a flare so predictable that astronomers have mapped its path centuries into the future. The sheer violence of these encounters is hard to overstate. As the smaller black hole smashes through the gas disk at nearly 1/10 the speed of light, it creates shockwaves that ripple outward, launching jets of plasma hundreds of thousands of light-years into space. The resulting flash outshines the galaxy's stars combined, visible across the universe. What's astonishing is how cleanly the system follows Einstein's predictions. The flares arrive within 4 hours of their scheduled time, a testament to how precisely gravity governs even the most chaotic cosmic events. Yet these binary black holes are racing against time. With every orbit, they lose energy through gravitational waves, inching toward an inevitable collision. When they finally merge, in roughly 10,000 years for OJ-287's pair, the resulting explosion will unleash more energy than all the stars in the observable universe combined, shaking spacetime itself. Until then, they offer a rare glimpse into the late stages of a cosmic duet, proving that even the universe's most destructive forces can move with eerie clockwork precision. The implications stretch far beyond a single galaxy. If close binaries like this are common, they could explain why some galaxies have oddly shaped cores or mysterious gaps in their star distributions, traces of ancient black hole encounters that reshaped their homes. Every time we spot another of these pairs, we're witnessing the aftermath of a galactic merger, a snapshot of how the universe builds its largest structures through violent, inevitable collisions. And in their final moments before they vanish into a single, more massive black hole, they put on a light show that defies imagination, a celestial fireworks display timed to the heartbeat of gravity itself. Humanity's greatest power sources might not be found on Earth or even in stars, but in the swirling depths of a spinning black hole. The secret lies in the ergosphere, that twisted region just outside the event horizon where spacetime itself gets dragged around like water in a whirlpool. Here, the black hole's rotation is so violent, it warps the fabric of reality into a cosmic energy farm. The process, dreamed up by physicist Roger Penrose in 1969, sounds like pure science fiction. Objects entering the ergosphere could steal energy from the black hole's spin, emerging with more power than they arrived with. Imagine a spacecraft diving into this gravitational maelstrom, splitting in two so one piece falls past the event horizon while the other escapes, carrying away energy stolen from the black hole's rotation like a cosmic bank heist. The numbers defy belief. A single supermassive black hole like Sagittarius could theoretically unleash up to 20% of its total mass as usable energy. That's thousands of times more efficient than nuclear fusion. Compare that to our Sun, which converts less than 1% of its mass into energy over its entire lifetime. The Penrose process essentially turns black holes into universe-scale batteries, their spin acting like a winding mechanism storing unimaginable power. Futurists have even speculated about advanced civilizations building Dyson spheres around black holes not to capture starlight, but to harvest this gravitational energy on an industrial scale. Instead of delicate solar panels, these megastructures might feature colossal energy taps plunging into the ergosphere, siphoning power from spacetime itself. Yet the engineering challenges are as vast as the rewards. To extract energy this way, you'd need to precisely time the breakup of matter entering the ergosphere, ensuring the escaping fragment carries just the right momentum. One miscalculation, and your entire apparatus gets shredded by tidal forces or lost beyond the event horizon. Some theorists suggest an alternative firing charged particles into the ergosphere where the black hole's magnetic fields can accelerate them to near light speed, creating energy beams intense enough to power interstellar civilizations. Others imagine vast Penrose reactors where controlled streams of matter spiral into the ergosphere, emerging as high-energy plasma to be captured and converted. The craziest part, we've already seen natural versions of this process at work. Quasars, those brilliant beacons from the early universe, likely owe their incredible luminosity to energy extraction from spinning black holes. Their jets acting like unintentional Penrose processes on a galactic scale. If nature can do it accidentally, could we one day replicate it deliberately? The answer might determine whether humanity remains bound to the tiny fraction of energy stars provide, or unlocks the true power hidden in gravity's darkest engines. What if everything inside a black hole, every atom, every star, every shred of existence it swallowed isn't lost at all, but etched onto its surface like a cosmic tattoo? This mind-bending idea, called the holographic principle, suggests black holes might be nature's ultimate storage devices, encoding three-dimensional information in two dimensions. Picture dropping a book into a black hole. Instead of being shredded beyond recovery, its contents could be perfectly preserved as flickering quantum patterns on the event horizon, not as words on a page, but as fundamental vibrations woven into the fabric of space itself. The roots of this theory trace back to a fiery debate between Stephen Hawking and Leonard Susskind. Hawking famously argued black holes erase information, vaporizing it into random radiation. Susskind countered with a radical notion: what falls into a black hole isn't destroyed but smeared across its surface like ink on a balloon. The holographic principle takes this further, proposing that the entire three-dimensional interior of a black hole, its crushing depths, its hidden singularities, could be represented entirely by quantum data dancing on its two-dimensional boundary. It's as if the universe runs on a cosmic projector with black holes serving as the ultimate screens, but the implications stretch far beyond black holes. If the holographic principle holds, it could mean our entire reality operates like an illusion, a three-dimensional world emerging from a two-dimensional code at the edge of the cosmos. Imagine your body, your thoughts, the room around you, all just shadows cast by interactions on some distant, unimaginable surface. This isn't philosophy, it's hard physics. String theorists have shown mathematical links between equations describing events inside black holes and those governing particles on their surfaces, suggesting information isn't lost, it's transformed. The most tantalizing evidence comes from entropy. Black holes have entropy, a measure of hidden information directly proportional to their surface area, not their volume. It's as if everything inside leaves a fingerprint on the outside. When two black holes merge, their final event horizon area is always greater than the sum of their parts, preserving the total information in the universe like a cosmic ledger balancing itself. Even Hawking eventually conceded, revising his theory to suggest black holes might encode information in their radiation after all. Could this holographic nature extend to the entire universe? Some models suggest our cosmos might be a projection from a two-dimensional shell at the edge of spacetime, with every event, every particle, just pixels in a vast cosmic display. If true, black holes aren't just cosmic oddities, they're windows into reality's deepest secret. That dimension itself might be an emergent property, not a fundamental truth. The next time you look at the night sky, consider this: the darkness might not be empty at all, but a canvas vibrating with the hidden code of everything that ever was. We've journeyed to the edge of physics and peered into the abyss, discovering that black holes aren't just cosmic vacuum cleaners, but reality's ultimate rule breakers. They warp time like taffy, turning seconds into centuries for distant observers. They spin so fast they twist space-time into knots, creating energy farms in their ergospheres. Some might even be holograms, encoding 3D information on 2D surfaces like cosmic flash drives. And let's not forget their appetite, swallowing stars whole, then belching jets of plasma that stretch across galaxies. These gravitational monsters force us to rewrite the rules at every turn. Einstein's equations break down at singularities. Quantum mechanics clashes with relativity at event horizons. Even something as simple as information becomes a paradox when black holes enter the picture. Yet this chaos is precisely why they fascinate us. Black holes are the universe's greatest thought experiment, laboratories for testing ideas about wormholes, dark matter, and the nature of space itself. So tell us, which fact left you rethinking reality? Was it the way black holes turn people into cosmic spaghetti, the possibility of hidden universes inside them? Or that eerie B-flat humming from Perseus? Drop your mind-blown moments in the comments, and if you're hungry for more mysteries of the cosmos, hit subscribe. The universe has plenty more secrets to share, and we're just getting started.